Assalamualaikum and hi, my name is Siti Aisyah binti Sunarno with metric number 192163 from Bachelor of Electrical and Electronic Engineering. In this video, I'll presenting my final year project entitled Modeling for Interacting Series Process Plant using System Identification Method. So this is the outline of my presentation. I'll begin with introduction, problem statement, objective methodology, result and discussion, and also the conclusion. For the introduction, I'll talk about the Prospati 3 reactor, or RTP, which is the plant used in this project. It is the only nuclear research reactor in Malaysia, which is a pool-type reactor. It has started its operation in 1982 and reached its first critically on 28 June 1982. Its core sits at the bottom of a 7-meter high aluminum tank. It uses solid fuel element, which is zirconium hydride moderator enriched uranium with 1 megawatt thermal power. It has boron carbide control rods, and the reflector is a graphite. So the problem statement in this project is about the simulation model of RTP system have been developed in the Simulink lab. The simulation model development is based on the research reactor mathematical representative and the real plant parameters of RTP. So the challenging issue in this with research reactor is the time variation and uncertainty. Therefore, a model of RTP cooling system will be developed for advancement of system monitoring. The present studies aims to carry out an analysis for better understanding of the RTP cooling system model simulation through validation system identification of interacting series process plant. So the objective of this project is to investigate the mechanism of RTP cooling system, to develop modeling of RTP process control using N4SID, to develop interacting series process of cooling system using Simulink simulation. So next I'll talk about the methodology in this project. So the concept of RTP cooling system is actually the primary coolant circuit is the secondary cooling circuit is two coolant circuit that exist in RTP cooling system. The output parameters is the temperature, pressure, and flow rate. The primary cooling system is to take about water out from the reactor tank and secrete it through heat exchanger and returns back into the reactor tank. While the secondary cooling system is the heat from the primary coolant circuit which is transported to the environment. So this is the structure of RTP cooling system. So this is the overview of RTP cooling system. It involves valve, heat exchanger, demineralizer, and which has its own function to ensure the RTP cooling system works perfectly. While the other diagram is the block diagram of RTP cooling system, which include the cold heat exchanger, hot heat exchanger, and the reactor. It shows the output and input parameters of that subsystem. Okay, next is the modeling of reactor. It is based on analysis from reactor block diagram. The response changes on each of the sensor and considering the interaction from one to another output variable. The dynamic of reactor subsystem created, the transfer function of I input and J output, also the transfer function of I output to J output is created. It is using the MIMO model structure equation of 3 inputs and 2 outputs. So this is the dynamics of reactor subsystem, which include the input and output parameter, where we will get the transfer function of G11, G21, and so on. Same goes to the modeling of its exchanger. It has two models, which is two mathematical models, which is rate of change of hot field and also the cold field. The same method applied to reactor has been applied to both heat exchanger, while with a few modification of 4 inputs and 2 outputs instead. So this is the dynamic system of the cold and hot heat exchanger, whereas we can see the output and the input parameter. So, how the modeling of RTP cooling system have been done? First of all, we use the data collection, which is accumulating real data from nuclear power plant. Then we normalize the data so that the data fall in a same range to get a good data model. The model structure is using numerical subspace, state space system identification, and 4SID algorithm. It will interpret in transfer function. The model estimation is done by using the system identification toolbox, where the when we get the low MSE it can consider as a good model. The model validation is about comparing the model response to the measure response, analyzing residuals, and analyzing model uncertainty. So in this project, I used two things, which is to compare the model response to the simulated response, and also using residual analysis. For the result, I will talk about the reactor model. Heat exchanger model for hot and cold, which is I'll compare about the simulated response to the real operation response, and also talk about the residual analysis. So this is the reactor model, which is reactor model. When we get the dynamic system, we will try to find the transfer function, which is have the best fit of 90% and above using system identification toolbox, and we will plug in the transfer function into the subsystem like this, and we will run the simulation in Simulink, and we will get the output of T2 and P1. So output we will compare to the real operation. This is the comparison of real operation data with simulated data for T2 reactor. Okay, as we can see, at the beginning, the data fits perfectly towards the targeted data, but at the 58 seconds, it's increasingly because we can see it has uncertainty in modeling, which will affect to the increasing. So this is the result for the P1, which is at the beginning the data fits perfectly to the targeted data, but increasing at some times because uncertainty in modeling. For the hot is exchanger model, is we also apply the same method and we will run and we'll get the T5. So this is the result for the output P4. We can see that for both P4 and T5, the model response falls into the range and almost fit the data excellently. It means the model accuracy is high. For cold heat exchanger model, this is the output for the T3 and this is the output for the P2. It is low, has a low accuracy model. It fit the data at the beginning, but at the end, it diverting the fitness at the end. Because we can see here, because there's uncertainty, maybe there is the problem in the data because no modeling will be perfect. So for the residual analysis, it is regarding the residual properties of simulation data and measurement of real data. It has the benchmark, which is with A rank. The percentage must be below than 10% and B must be 10 until 20%, which is D will be more than 50%. So in this project, the reactor and the hot exchanger has a lower than 10% residual analysis, while the cold heat exchanger has more than 10% residual analysis in ranking B. So in conclusion, the modeling of reactor and exchanger is done successfully. It can be seen that the model response fall into respective range of good and acceptable model data. And for the future work, a much better accuracy can be implemented, as well as the whole system modeling shall be connected to each other for more accurate model response. So that's all from me. Thank you very much.